morning in Taiwan. It's 10 o'clock now, but I think 10 o'clock in the evening in Ohio. And we are very happy to have Professor Han to give a lecture on this series, which has to do with the idea of establishing a tsunami early warning system. Yeah, either based on the ground-based and sea-based, and most importantly, space-based systems. Integrate them. Hopefully, one day we could apply it to the Asia region. We understand that similar things have been kind of established in I think in America and Europe, but not yet in Asia. So we hope to try in that direction. And Professor Shin-Chan Han, he got his bachelor degree from the Seoul National University in I think in geodetic science, right? And he went to Ohio State to obtain his master degree and PhD degree in geodesy and geography. So he has done a lot of work on the GRACE mission. Yeah, and I glanced through his list of publications. There are some very interesting papers. In case you are interested in what his work have been covering, you should check his publication. But just about 2 months ago, he moved from Australia back to his home university, Ohio State, and now he's a big professor there now, no longer a student. And other thing important to us is that he is an expert on the CubeSat measurements of the ionospheric signal caused by tsunami. He has probably a number of quite interesting papers. I would say almost standard papers in the field. So we welcome Professor Han, please.
Okay, thank you very much, Professor Ip, once again for this opportunity for me. Firstly, to know this union, Taiwan Space Union, and secondly, the AOGS initiative you are leading. This is really well aligned with my future research and the current research and future direction. Also, what I found is the website, Taiwan Space Union website is really useful even for me. It has a lot of lecture recorded. Many are very useful. A lot of things to learn directly from the video recording. So that was a really useful material to me as well. I wish I can contribute a little bit to that record by having today's presentation. Okay, so I guess I need to share my screen. So my name is Shin-Chan Han. If you know, of course, many of you know the traditional Chinese character. This is how I write my name in traditional Chinese character. Today I will be talking about 4 different geodetic satellite systems, which measures ionospheric perturbation after the Tongan volcanic eruption. The first kind of geodetic ranging system is GPS. I am particularly interested in CubeSat-based GPS tracking. Why? This is so cheap to make a measurement. That means we can make a lot of CubeSat, which has a GPS tracking to do many number of radio occultation data analysis available from large constellation of CubeSat. So this is one technology, low-cost technology I like to focus on today. Basically, how good GPS data is with regard to detecting some traveling ionospheric disturbance anomalies associated with the geohazard, including volcanic eruption, earthquake, and tsunami. Second type of geodetic ranging system I'd like to show you is GRACE K-band microwave, dual frequency microwave. The Grace Farlow has a laser, but laser is not useful for measuring anything regarding to electron density. But Grace Farlow has a primary science payload, dual frequency K-band microwave. So I will show you a very nice data set we got from Grace Farlow on K-band tracking data. The third, satellite altimeter, which is also use a microwave like the Ku band and C band. This is for measuring the height, elevation of the satellite from the sea surface by making a microwave ranging distance measurement between satellite antenna here to the ocean surface. It is also using dual frequency radar microwave, Ku and C band. That means we can retrieve the electron density along this microwave propagation path between the satellite and the ocean surface. I will show you some example of TID measured by this altimeter satellite system. The last one, probably not many, I mean, some of you may be aware of this system, but not all. The DORIS is basically we call GPS upside down, because the transmitter is the ground beacon in the station distributed in the on land, and this ground station is transmitting the S-band and VHF radio signal, and DORIS receiver on LEO satellite receiving the range rate data between the station on ground and the satellite, which also has information about the ionospheric perturbation. Okay, so I am a geodesist. What is geodesist? Who are they? So we are working on the problem like Earth's rotation and shape of the Earth and gravitation of the Earth. These are three major topics geodesists are working on. And geodesists, many geodesists, not just me, are typically heavy on measurement side, not just the data processing, but also thinking about new instrumentation, new way of measuring geophysical signal, the different method, and also the mission design is also covered by the tasks by geodesists. Then this is also what I'm interested in. I do a little bit of modeling. So I can say maybe the 75% of my research is about the data, 25% is a little bit of modeling. So this talk I'd like to focus on the measurement, and I give you a little bit of the qualitative the interpretation of the measurement at the end of this presentation, but mostly I'll be talking about various kinds of measurement of TID induced by the volcanic eruption and tsunami. So geodesists encounter space weather. So I have two different plots. The one is old geodesists, our ancestor. So they are doing some measurement using sticks and plummet. So they are trying to measure, this particular picture is from the French geodetic expedition. So they are trying to measure the meridional arc length to prove the Isaac Newton's idea of oblately flatten the Earth. He drove this model of oblate shape of the Earth. And Newton also had an idea about the surface gravity may be dependent on the latitude because of its shape. So shortly after Isaac Newton died, they made French king actually had the team of geodesists, surveyors working on, the measuring the meridional arc length. And this particular picture highlights the aurora. So these people are working under the light of aurora. So space weather, geomagnetic storm, solar storm is basically helping them to make a measurement during nighttime. So now we are doing much more complex steps. the Earth is rotating like this. By the way, do you see my cursor, the pointer? Yeah, I'm assuming you can see my pointer while I'm talking.
We can.
Okay, great. Thank you very much. So the Earth is ellipsoidal shape like this, but there's a lot of things going on. For example, Antarctica ice is melting. We are losing a lot of ice from Greenland, Western Antarctica, particularly in Alaska. So these melt ice goes to the ocean, and sea level rise, and there's a water cycle between the atmosphere and the land and ocean. And also these mass redistribution, like ice mass at the pole going into the ocean, so mass redistributed from the pole to the lower latitude, then makes the Earth's rotation wobble. And that Earth's rotation wobble changes the centrifugal force, correct, centrifugal acceleration, and the ocean is responding to that, and it also lowers the elastic Earth. So there's a lot of complex things are going on, and what I'm trying to say here is we can measure the subtle change in the shape and gravitation and rotation of the Earth. So now we are looking at the small change of this rotation, shape, and gravitation of the Earth, and those changes are primarily driven by Earth system change and climate change. So what kind of measurement we are using in contrast to our ancestor surveyors are using, the stick and plummet. We are using mostly microwave and laser distance measurement. And for that, space weather, ionosphere is not helping us. So you have to do something about that to get what we want to measure using this microwave and laser-based instrumentation. On the other hand, we can use this geodetic ranging system to study ionosphere, and we found that we can look at this instrumentation to see the perturbation in ionosphere, and that perturbation could be introduced by the sun or the phenomena happening on the Earth. My research interest is the ionospheric perturbation caused by the phenomena on the Earth's surface. So CubeSat, I'll be showing some of the decent CubeSat GPS measurement next few slides. So several years ago, I encountered with this, a small satellite, but at that time I was not really convinced whether this small patch antenna on this little, tiny CubeSat is really producing something useful for science. I was kind of, I wasn't sure about that. So what I probably 2021, I started to look at this GPS data myself. So I will show you some of the GPS LEO here. LEO means the CubeSat, high-load tracking data. So basically, I'm looking at GPS data between, the GPS carrier phase measurement between GPS satellite here, 20,000 kilometers above the Earth's surface, very far away, and 500 kilometers above the surface LEO, here CubeSat. So for positioning, we are using this signal directly above the CubeSat, but for looking at the atmosphere, we are measuring the satellite on the horizon or even below the horizon. We can measure the signal coming from the satellite below the horizon because of refraction. So this refraction is, as many of you already know, is due to the amount of electron along the signal path. So if you look at CubeSat data and try to process this TAC data by combining, the Earth frequency, very typical processing method, you can get something like this. This is the first result I got from the GPS CubeSat data analysis So I was really convinced. After I saw this, I was really convinced that CubeSat is not toy. This is some small economic payload that we can do science with. So the blue dot shows CubeSat recovered the electron density profile from roughly 100 kilometer to the satellite altitude, which is 550 kilometer. The red is the model prediction, in this case, empirical model, International Reference Ionosphere. And one of my colleague, Colin Water, processed the ground ionization measurement, which is in here in green. He found that there's a bias, but all three seems picking this F2 layer major peak really nicely. Also, the another peak, in layer peak below the F2 layer. So, looking at this one, I convinced this CubeSat data set. So I tried to look at further. So this is another striking result that I got in the beginning of 2022. So just after Tonga volcanic eruption, I tried to look at some CubeSat measurement around the region. So this is the before the volcanic eruption. The CubeSat was here. This is about maybe 20 minute or 30 minute data. This is 20, 30 minute trajectory. And GPS satellite must be somewhere here. And we are looking at some kind of electron profile around this tangent point by assuming, this calculation can be done by assuming the electron density change with the altitude. There's no lateral change. By assuming that, you can convert the measurement from CubeSat and GPS, the LEO, CubeSat and GPS to CubeSat, to this electron density profile, vertical profile, this representative point. So basically, this you can consider this is one representation of the GPS measurement. Compared with IRI, a pretty decent match in terms of magnitude of electron density and the peak location. So okay, but just after volcanic eruption, so basically this is gone. So IRI has nothing to do with volcanic eruption, so it predicts, just the standard variability, but CubeSat measures gone. Electron density was completely disappear in this region at this particular time. So this result was interesting enough for me to spend more time about this event. So I have a bunch of data I'd like to show you. I'd like to share with you to emphasize how good these CubeSat GPS measurements are. So I'm not going to talk a lot about this Tonga this HTT volcanic eruption. The one thing I'd like to point out is that there was a ocean wave. It's a little bit confusing. It looks like a tsunami, but it's not really tsunami in classical sense, classical definition. There was a wave arriving faster than the classical tsunami, with the speed of about roughly 300 meter or 350 meter per second. This is due to atmospheric pressure loading induced sea level change that is propagating along with the land wave. So that was arrived on land before tsunami arrived. Tsunami is about 200 meter per second. So if you look at the CubeSat measurement, you can measure the history of this wave arrival introduced by land wave, ocean wave loaded by land wave, and followed by tsunami wave introduced the perturbation, something we can measure. I'd like to show you this result in a minute. So if you look at CubeSat data, so this shows this particular time, UTC, this is a GPS number 30. Blue shows a CubeSat trajectory, 14th of January, red, 15th of January, volcanic eruption happened 15th of January, by the way, and yellow, 16th of January, And the bottom plot shows the total electron content measurement between GPS 30 and CubeSat along this trajectory. So the 14th one here, okay, so very smooth change, primarily changing with elevation. So this color shows the elevation of a GPS satellite seen from CubeSat. So CubeSat is here, so GPS satellite is above the CubeSat, so elevation is basically 90 degrees. CubeSat is looking at GPS satellite from here, so elevation of this satellite is pretty low. So we are talking about a wide range of elevation change due to fast movement of CubeSat relative to GPS satellite. So, this case, pretty normal. Everything is changing largely with the elevation change. This one is also pretty normal, except the end of this red trajectory here, which is 15th of January, on the day of a volcanic eruption. There's a tiny bit of a perturbation. I should not say tiny bit, but magnitude of perturbation is pretty big. Several TECU, huge signal. And if you look at, you come closer to the event location, and there are, oh, by the way, this is one CubeSat approximately repeating the same location, same time, roughly speaking, 3 different days. So the same satellite is looking at perturbation like this before the volcanic eruption. On the day of volcanic eruption, you have a wide range of perturbation. Magnitude is maybe 5, 6, 7 TECU, and the day after is relatively smooth. And so this satellite, this GPS satellite, and that CubeSat is also picking up some perturbation on the day of volcanic eruption. So if you play this and look at the transition of the GPS measurement from different satellite, different CubeSat, so at different time. So this is the time period from 4.0 to 4.8 hours in UTC. Next one is 6 hours, roughly 6 hours, and this one is similar, and this is 8 hours. CubeSat was flying from west to east. In this case, the color represents hours in UTC, not local time, but UTC. And red shows GPS location, GPS trajectory, ground track during this period of time. And this time, eruption didn't happen, so this is before the eruption. If you look at the CubeSat measurement, GPS measurement, nothing other than change, the large change associated with the elevation change. Okay. If you look at the second one, this is right after the volcanic eruption. The cyan color here shows the LAM wave propagation. So this outer circle indicates the LAM wave, predicted LAM wave location at the time of 6.7 or something like that. Inner circle indicates the LAM wave around 5.8 hours or something like that. And I had one particular cube, so I forgot which one, like this. And if you look at this trajectory along with the TEC measurement from the GPS, you can measure the width of the LAM wave propagation by looking at the anomaly in GPS measurement. And that width is pretty much consistent with the speed of the predicted LAM wave perturbation outward from the event location. And same here, different satellite, different CubeSat, you get a pretty decent measurement. And by measuring this, you can see how the land wave is propagating by perturbing the ionosphere. This example is likewise at hour 8.3 or something, land wave propagate all the way to covering more than East Australia here, right? And you have a perturbation as large as several TECU. It continues, so land wave propagate outward over time. And then if you look at the CubeSat crossing the land wave, you can see half of them clean, the other half is perturbed because this is, the CubeSat is measuring ionosphere over the region where land wave passage is swept. So there's a clear indication of this perturbation is associated with the land wave propagation, perturbing the ionosphere. So you can do this data. You can play with more data, and I was looking at antipod approximately 14 hours after the land wave approached the antipod from this event location, which is north of Africa. So you can see, the ionospheric perturbation as large as 5 TECU. There's a little bit of a similar perturbation before the event. These are the same pair of CubeSat and GPS, by the way. The left indicates the measurement before, on the day before the event, the volcanic eruption, and the right panel shows data set on the day of volcanic eruption. So you can see, a few TCU size of perturbation, even in the antipod of the event location, even after 14 hours later. This is a pretty significant perturbation. And I did, this is for fun, I did put everything available. So at this time of the data analysis, I think there may be 10-ish or 10 or 12 CubeSat available and different inclination, polar orbit and equatorial orbit. So I did some automatic search of high frequency TID perturbation, and if there's some high frequency perturbation, I make a color of that event existing in CubeSat GPS measurement. So basically, I can see this constellation high frequency anomalies are following the land wave propagation through the measured through the CubeSat orbit. One thing I think very interesting is, I'm not sure, this is the another high frequency anomaly I also observed from this polar inclination CubeSat is anomaly appeared in the Antarctica. Some of them is same time as the main perturbation associated with the land wave. I wasn't sure this may be possibly related to conjugate effect. Yeah, this is something we need to look at further. So if you look at this measurement in the context of tsunami, so here, this is one particular CubeSat trajectory and land wave during this time, during this time of the day, 7.4 hours all the way to 8.3 hours. So 8.3 hours, land wave approached the outer circle. In the beginning, it was inner circle. And tsunami was behind of the land wave because this is propagation speed is lower. I look at the different GPS satellite and one CubeSat and plot everything together along the longitude and try to find out which one is land wave, which one is tsunami. It was a little bit hard, but this method, the same data set, presented a different way. So I did the high pass filter and look at the not just this elevation dependent anomaly, the change, just focus on this high frequency perturbation in the data and try to see each wave, the characteristic speed of each wave by plotting, distance and time plot of the anomaly. And I found some of them are likely introduced by tsunami, and many of them are, the LAM wave. So this case is primarily the LAM wave introduced to the perturbation measured by CubeSat, looking at the many different GPS satellites, followed by the tsunami one. Okay, I think I'm going to show you this one by skipping the previous one. So I think this is really cool in a sense that how we measure the ionospheric perturbation introduced by this LAM wave propagation. This is a little bit complex plot, but this is interesting enough. So please be patient and try to follow me. So this dashed curve shows the LAM wave front at the time of UTC 13.30. And I found one CubeSat crossing the LAM wave from west to east. Right? And this trajectory is the CubeSat flying module 119 on the day of eruption, and the same flying model, slightly different ground track the day after. And interestingly, this CubeSat has an antenna looking one side, and the other antenna looking the other side. So the same CubeSat was looking at GPS satellite one side, exactly same satellite. The antenna is looking at the GPS satellite here, the other side. So basically, one satellite is measuring the atmosphere before the LAM wave passage, and looking at the other antenna, this satellite is measuring the atmosphere after the LAM wave passage. So red indicates the data outside the LAM wave passage. Blue indicates the data inside the LAM wave. So if you look at the blue data inside the LAM wave, on the day of volcanic eruption, you get a pretty small variation of electron density over altitude. If you look at the same data but different day, you have this much of very typical distribution of electron density. And if you look at the outside of LAM wave, there's not much reduction as much as this. So this is a pretty cool demonstration of measuring ionospheric perturbation from one satellite, but pristine condition and the perturbed condition together simultaneously. Next set of data set is from Grace Farlow. As I mentioned, it is a K-band and Ka-band dual frequency tracking each other. Satellite to satellite separation is roughly 220 kilometer. Altitude is roughly 500 kilometers. So dual frequency microwave ranging is providing us TEC integrated over this short baseline, like 220 kilometer. This was pretty useful. Here is the Grace track. This is ascending track from south to north. 3 different days, 14th, 15th, and 16th. And local time, UTC this time. And obviously this shows a magnetic equator. So at this time, particular time, 3 different days, the Grace measure TEC, very typical, it's very strong around the equatorial region, a little bit extended farther south. On 15th, volcanic eruption day, at this particular time, LAM wave propagate all the way to here. This is still measurement outside the LAM wave. The LAM wave didn't approach yet the atmosphere grace measured. So everything looks normal. So things are electron density in terms of TCU here is pretty normal. The largest electron density appear the equatorial region, magnetic equator, by the way. Gray shows the day before, red shows volcanic eruption day, black shows the day after. Different next orbit. So basically, the Earth is rotating from west to east. So I intentionally made this ground track as center. So you see the background map is moving while Earth rotates, right? So Australia is here, now here, after one orbit, roughly 90 minutes. And land wave propagate this much, okay? So at this side, Earth is rotating this direction, RAM wave is propagating that direction. And the grace is sampling the atmosphere westward. So this case, I see huge reduction, almost 3 order of magnitude reduction. How much wide? Maybe plus minus 15 degree. 15 degree north from magnetic equator, 15 degrees south, magnetic equator reduction, as much as 1,000 times of electron density is gone, and very wide area. Likely introduced by this Lamb perturbation. Here, basically the grace, the Earth's rotation is faster than Lamb wave propagation. So the grace is really catching up the westward propagation of Lamb wave. So next orbit shows the sampling in this area, and you can see the similar reduction. And the orbit after, the one orbit after, the Lamb wave propagate all the way to the Western Australia here, and grace sampled this one. You see a little bit less, but still significant the reduction. But what's interesting to me is some kind of a positive increase along the magnetic latitude. This was pretty interesting feature to me. I'm not sure the reason yet. And next orbit is at the boundary of Lamb wave, the one after outside the Lamb wave. So basically, this shows a transition of grace measurement, starting from the inside of Lamb wave passage and catching up the westward propagating Lamb wave, and finally it measures the outside of Lamb wave because our rotation is faster than Lamb wave. So we can measure inside and outside from one satellite pair like grace. This is another pretty interesting measurement. Size, the key message is the size is about 2 or 3 order of magnitude reduction at the altitude of 500 kilometers. Perhaps a little bit of increased electron density at the roughly plus minus 15 degree north, 15 degrees south magnetic latitude. Third example is the geodetic ranging system we call satellite altimeter, which measures distance from the antenna here all the way to the surface of the ocean using KU band and C band. Satellite altitude is roughly 800 kilometers higher than grace and CubeSat. So TEC is basically integrated electron content between 800 kilometers to the ocean surface. So if you look at the raw data, which is shown here as a dot, and then I made some smoothing, which is in magenta here, and I plot the measurement, original blue dot, and smooth it, magenta curve, along with 2 model, GIM, global ionosphere model, and NIC is another alternative model used for satellite altimeter ranging correction. The day before, on the day of volcanic eruption, the day after. So 3 different tracks, and this is the Lamb wave passage. Lamb wave passage at this particular time, and only this measurement on the day of volcanic eruption, we observe a pretty significant reduction. How much compared to the other days? Here, maybe 10 TECU. The reduction of electron density from 800 kilometers all the way down to ocean surface. Obviously, the model has nothing, that doesn't do anything about this depletion. What is also interesting to me is that this descending track, the other track. So the significant reduction, but the two peaks at the edge of this depletion, we have enhanced the electron density. I will come back to this one a little later. So we can do these steps with different measurement, line wave propagation. We have a pretty consistent depletion as wide as 30 degree or even larger in longitude, which means we are talking about 3,000 kilometer or larger latitudinal band of electron depletion introduced by the line wave perturbation. The last example is Doris. So this is current updated distribution of ground beacon. So there's a station disseminating all the microwave, S-band, and VHF radio upward like this. And then there's a satellite which has a Doris receiver. Doris is acronym of this, which measure line of sight range rate between the ground station and the satellite LEO. So basically we are measuring TEC from ground to LEO satellite. All right. So this is another technique we are using for positioning and all other geodetic application. The ranging system is called Doris. You can use it for looking at the ionospheric deflation. The same story. This is a line wave here at this particular time, and if you look at the ionospheric delay measured by this dual frequency measurement here, and that delay is caused by the refraction, caused by the electron density. So this is very typical. This U-shaped change is very typical. Electron density changes like this, primarily dependent on the elevation of satellite seen from the ground station. But here is the elevation. Okay, so day 14 track like this, LEO, and this particular station, we call BTB station here, sees this satellite with this sort of elevation change. 15th is a bit closer to the site, so this is a larger elevation change. So, but we don't see much of the delay. That indicates, the ionospheric delay, small ionospheric delay change indicates the electron density is pretty much depleted. If you look at the similar area 12 hours after, we found the satellite track like this, same station and same satellite, Jason 3, but 12 hours later, things are normal, everything is normal. So I'm going to skip this. It's the same message, so I don't have much time. So one we think is probably many of you heard about this effect, E cross B. So we believe Tonga events generate the neutral wind this way, and there's a daytime, nighttime contrast in conductivity, and that is coupled with this wind, and we have generated a dynamo-electric field like this, and this electric field is coupled with magnetic field. So it can push all the electrons upward and the electrons can diffuse to high latitude from magnetic equator, and it is accumulated roughly 15 north and 15 south. I think this is what we see from Gray's here, two peaks roughly around plus minus 15 north and south. Also altimeter data looked a little bit higher than 15, but maybe roughly 18, 19. Yeah. So I think this is something we see from the older geodetic measurement. So basically, this E cross B uplift forcing pushes the electrons upward and diffuse to high latitude area. So this area is pretty much empty, and all the electrons are accumulated in this particular latitude. So I will spend some time. I don't have enough time for talking about the tsunami. Probably I will quickly introduce some of these slides I prepared. So basically, this team thought about this problem many years ago, almost 20 years ago, by using global normal mode calculation, and they found like a high frequency short wavelength ocean swell. It cannot be propagate upward and perturb ionosphere because wavelength is too short. But the tsunami is a right wavelength, which can perturb ionosphere through some coupling. So they had a really nice discussion, theoretical discussion about this coupling between the tsunami and the atmosphere at very particular frequency and the wavelengths. So this is dispersion curve, the temporal frequency and angular order means the basically spatial size of the wavelengths. So what they're saying is this particular frequency band, like 1.5 millihertz, roughly 2 millihertz, 2.5 millihertz discrete band, because they assume one-dimensional Earth coupled with the ocean and coupled with the atmosphere together. So at this particular frequency band, the tsunami energy can propagate all the way to the atmosphere. Split of the energy could be as large as 50-50. Okay, so they have some nice modeling and data analysis, which fits pretty decently with the GPS measurement, which is in black, I believe, and the model, normal model, red. They had to adjust a little bit in timing because their calculation is based on 1D Earth model with the uniform ocean thickness, but the actual ocean is not uniform. And tsunami wave speed is changing in the open ocean primarily with the thickness of the ocean. So other than this small change, a little bit of calibration to reflect the 3D, the realistic Earth. The magnitude and time, the phase and shape is pretty well agreed between the model and data. As you can see, this was a pretty big earthquake, Tohoku-Oki earthquake, and the tsunami was as high. Oh, tsunami was not that high, several centimeters according to the RTV data. It is generating less than 1 TCU perturbation. This is another extension of their study. They found the cosmic GPS radio occultation data. Background signal is as large as 300 TCU, but the tsunami signal from this giant megathrust is only 1 TCU. So, but they got some really decent modeling in comparison with the data, but we are talking about small fraction of anomaly introduced by tsunami relative to background the electron density distribution. We are talking about less than 1%. So we did another modeling. This is courtesy of Xingmeng, University of China Science Technology. She had us 3D. At this stage, this is not spherical model. This is non-spherical model, 3D wave propagation was done by my colleague, and very nicely reproduced the result they expected here. And the perturbation in terms of electron density is 10 to the, I forgot the exact unit. Yeah, but what I'm trying to say is the detection threshold is about 0.5, 10 to the power 10 electrons per either meter cube or centimeter cube. I forgot to add. Oh, here, there you go, meter cubed. So this is a detectable signal from current GPS data. So this is the summary. So it's the right time. So all geodetic measurements indicate pretty huge electron depletion as wide as 20 degree latitude, even larger, and the longitude about as large as 50 degree along the magnetic equator, and that depletion lasted almost 7 to 8 hours. So during this huge area, this long period of time, there's a huge depletion. I'm not sure any the previous solar storm event has such a large perturbation in the ionosphere. So, all the geodetic ranging system are indicating this perturbation is primarily associated with perturbation by Ram wave propagation. And this is a really nice demonstration that indicating the huge ionospheric depletion and perturbation change introduced by the surface, not the solar storm, but our surface event, hazardous, natural hazard event, like, in my case, volcanic eruption. Yeah, so, yeah, I'm going to skip this. The last one, I'd like to point out this. So the tsunami anomaly, we can measure from current GPS radio occultation method. Even, the Tohoku large earthquake introduced big tsunami. We are talking about 0.1 or 1% of perturbation introduced by tsunami with respect to background electron density distribution. Generally less than 1 TECU, maybe a lot less than this. Detection is certainly feasible. Many ground station and satellite data is demonstrating detection of this small anomaly, but obviously it is desired to have some dedicated sensing system, maybe a little bit of a different setup of radio occultation. For example, LEO to LEO radio occultation, maybe one alternative technology or alternative sensing method for measuring the tsunami anomaly with better signal to noise ratio, signal to background signal ratio. So tsunami signal to background signal noise ratio, we like to have them high. So we can have some alternative design of measuring ionosphere, maybe better than GPS radio occultation. This is something I also am interested in working on toward this idea. Thank you very much for your attention.
Thank you very much for this very, I would say, very detailed lecture on what you have done with CubeSat. I have not realized that the perturbation is really that small, no less than 1%.
Yeah, compared to the background is,
Yeah, and with early warning, because we are concerned with the early warning capability. The question is, can you pick out this 1% or less than 1% effect real time or near real time? I mean, in let's say in 10 minutes, 20 minutes.
That's a yeah. In general, obviously it will be challenging, right? So this must be near real time, indicate meaning that either there is some. So probably I'll turn off the share. Stop presenting. So I guess either we process the GPS data on board on satellite, and do some onboard calculation, and if there's some signal greater than threshold, we receive that. That may be more effective way instead of downlink all the GPS data and processing on the ground. But the question is, can we have a good algorithm to detect tsunami almost near real time, even in onboard processing? So we are dealing with 1% of signal, so it'll be challenging. But together with the model and some matched filters, we can design some sort of a filter which can help us to make a decision whether there's a significant anomaly detected by tsunami or not, but in conjunction with the model calculation together. So, for example, if there's an earthquake or some other event, there's a preliminary earthquake solution, like a global central CMT, centroid moment solution. So this solution is available near real time, right after the earthquake. That solution has an indication of the event location and magnitude of earthquake. That can be input in the tsunami ionosphere calculation on board, and then we can make some model prediction together with the GPS data and design some matched filter. There might be some possibility, but in my opinion, looking at the modeling immediately after we receive preliminary earthquake solution, run the model together with GPS data, maybe one solution of making near real time warning. Or the other way is designing a specific, way of measuring this small tsunami or volcanic eruption or hazard event associated perturbation more effectively with the higher tsunami signal to background signal noise ratio. One of the examples is probably LEO radio occultation. Instead of GPS and LEO, we can have a radio occultation between two LEO satellites, which may deliver better resolution of a small anomaly. We can discuss many options.
Right.
Yeah.
That may should be the things that we need to discuss more. Any question from the audience? I see. Dr. 视频视频你在吗？
Have you, sorry, excuse me, because my connection is kind of lousy. Have you seen any conjugate effect of the land wave on the ionosphere? Thank you.
Yeah, that's a really cool concept. I had this discussion with the other colleague at Goddard. I believe he made the presentation recently in this TSE forum. This conjugate one was pretty good physical phenomena we may exploit for advanced warning, right? So signal is far away, but still we can detect the signal completely different location while the thread is away. So that one was a pretty decent one. So I guess, I'm not sure, I'm not expert on this, but if I may share again my screen, share screen. So some of the data I presented, here. I'm not sure this Antarctica anomaly. This Antarctica anomaly appeared along with this main anomaly by this LAM wave. I'm not sure this may be a conjugate of this one or not. So yeah. So for your answer, I'm not 100% sure, but I am aware of this conjugate anomaly thanks to the colleagues at Goddard I met a couple of years ago. And I believe we can exploit this conjugate phenomena for the advanced warning for of any event, like including tsunami.
Okay, thank you. And sorry, but I have another question is that the land wave will propagate through the Earth, then come back again for about 2 or 3 days.
Yeah.
Have you ever seen any more perturbations afterwards?
Yeah, that's also a great question. So I have looked at one cycle, so from the Tonga to the Antarctica. But there's a 3 cycle of this propagation. But I haven't looked at more than that. But probably if someone look at the CUBESAT data more, probably they may see further cycle more than one, which I have looked at.
Okay, thank you, sir. That's my question.
Thank you.
Professor Han, do you know Deng Sok Lim in Washington? Lim,
No.
R-I-M, Deng Sok.
Yeah.
He is a mathematician. He's working at, I think, in Washington University at St. Louis. And he will be giving a talk very soon because he is interested in using mathematical model to provide real-time, kind of near real-time warning. So I would inform you when his talk will be. It will be interesting that you'll be there and talk to him too.
Yeah, that will be wonderful. And once again, thanks for initiating this group within AOGS and TSU. It will be really, I was really glad to see this is happening.
Yeah, good. And by the way, Professor Lim, he's also from Korea.
Oh yeah.
I'll send you some information about him. Yeah, so that you can make perhaps connection. Since you are now already in America.
Thank you.
Any question from the audience? If not, because it's already 10 past 11, I think that Professor Han gave everything he has at this moment to us. We learned a lot, and look forward to seeing you and to listen to you again. Yeah, thank you. Yeah.
Thank you.
Yeah.
Bye.
Yeah, thank you, sir. Bye-bye.
Good night. Good night.